Okay, well, let's switch gears. So I'm going to just regale you with a few thoughts. Um, back in back in April, Ben invited me down to this shindig in San Francisco, and during the course of the evening, we got into a discussion about whether AI could scale indefinitely, and it was Ben's position that there should be no limit to how AI scales. And in the back of my mind, I was thinking about Jeffrey West's scaling laws. And I thought, I kind of suspect that since intelligence has grown up organically, there might be some scaling laws that apply to intelligence as well. If you're not familiar with Jeffrey West's scaling laws, I heartily recommend his popular science book, Scale. Um, he goes over scaling laws that apply to organisms, cities, and companies. I will just give a simple example for mammals. Regardless of the size and the metabolism, mammals have a fixed number of heartbeats. There's a constant number of heartbeats over the lifetime of a mammal. So whether you're a mouse with a very rapid heartbeat or an elephant with a very slow heartbeat, over the lifetime of those organisms, on average, they have roughly a constant number of heartbeats, which is the same. So that's one example of a scaling law, and there are many others that are really quite interesting. I heartily recommend that you take a look at his book. Um, my question was, are there laws of scale for intelligence? And I suspected that there might be. So here's kind of a back of the envelope argument. Um, we can imagine a population of agents. So when we think about agents, what we're talking about is some kind of computational process that's running on some substrate, right? And amongst those agents, if the population of agents gets so wide, in other words, there's lots and lots and lots of these agents in the population, then communication amongst them bears too many faults for all of them to agree on events. It's just like the whisper game. Some people call it Chinese whispers, some people call it telephone. But I'm sure you've all played that game where you sit in a circle, somebody initiates a whisper and it goes around the circle. And before too long, the message is so corrupted that it's simply unrecoverable from the original message. So again, this idea is relative to the computational and communication substrate that the agents are hosted on. The substrate itself will have hard physical limits for communication. So like if we're right up against the bare metal, i.e. physics, then that's speed of light. But we may be way, way, way far up the stack from physics. So for example, we're talking about ants as the computational model and pheromones as the communication medium. That the limits on messages and dispersal and things like that are much much slower than speed of light. And then how the computations are rendered to the substrate also provides additional inefficiencies, right? So those efficiencies add up to a limit on the rate of information flow amongst the agents. And that rate of information flow will create fault boundaries, right? So, and this is true regardless of whether we're talking ants or synapses or honeybees or satellite networks or traffic. Um, so the point is that the collection of agents, even if they're mobile, they naturally clump in terms of communication faults. And the clumps then have enough structure inside them because they're made of agents to become agents in their own right. Now notice that as soon as we've shifted to the clumping level to make our agents, the substrate for hosting the notion of agent has changed. So it's a very important point. But once you do that, then you can rinse and repeat, right? So that's a set of intuitions for a scaling law. Now, the question is, how do we code this up? Well, we use Erlang, of course. um, So here, I'm going to introduce a new family of row calculi. Um, so Weaver has his hand raised. Go ahead, Weaver. Did you have a question, Weaver? You're muted.
Yeah, sorry.
No worries.
Everybody use me now. I have another addition to this bunch of intuitions that about laws of scale. And it seems to me, I'm thinking about it a little bit like if you have a certain problem space, the points that allow you to find solutions that are with scaling up intelligence are like singularities on this problem inside this problem space, and I don't see how you can constrain the amount of effort, energy, and time to move from one singularity to the next one. So there is a certain kind of unknownability in finding the next step of scaling up intelligence. So just wanted to, and does not rely on physical constraints or something which is remotely even having to do with the physical constraints or substrate constraint.
Sure, sure. I see where you're driving at. I'm really just focused on like really, really low level stuff. I imagine there's a lot more phenomena that have to do with scaling of intelligence, but this is really just like brick and mortar kind of stuff right
Yes,
now.
that's my passion also, this open-endedness of intelligence. So I gave
Yeah,
some
yeah, yeah.
thought to,
Yeah.
anyway, thanks.
No, thank you. Thank you for the comment. Um, so just to model the kind of fault-based phenomena that I'm talking about. We're going to make a variant of the row calculus where the names for processes are not merely syntactic objects derived from the process structure, as you might find with the free model of row, but are the computable reals. So the at operator, which takes a process and delivers a name, is now going to take a process and deliver a computable real. And likewise, the star operator is going to take a computable real and produce a process. There are lots and lots of ways that we can do that, which I'll touch on in the next slide. But suspend your disbelief for a moment and just imagine that we can do that. Then we can use the arithmetic available to us on the computable reals to define a new class of communication regimes. So here we imagine that we've got some parameter delta, and when two reals, say R1 and R2, are less than delta apart, right? Then if I'm listening on R1 or if a process is listening on R1 while another process is sending on R2, since they're within delta of each other, we just do the normal communication, right? So Q gets passed along and substituted for Y in P. Now suppose, however, that they are farther away than delta. Then what we do is we reduce to an intermediate step. So we're going to rewrite R1 to R1 prime. Um, and oh shoot, there's a typo here. This should be R2 prime here. And R2 prime, R2 to R2 prime, where R1 prime is subtracting off delta and R2 prime is subtracting off delta. And then sigma is the substitution here. That's just affecting that substitution of R1 prime for R1. So we've moved this process over into the R1 namespace, and we've moved this process over into the R2 namespace. Um, and then we've introduced an error process. Um, so the error process, what does it do? Well, it has four components. It could intercept a message at R1 prime and drop it on the floor, or intercept a message at R2 prime and drop it on the floor, or it could intercept a message at R1 prime, shift it over to R1 double prime, which is just randomly moved over a little bit from R1 prime, and corrupt the message and then send that out, or vice versa with R2 and R2 prime and R2 double prime. So this is introducing both message corruption and message loss, right? And so what happens is the farther apart R1 and R2 are, more and more and more errors get introduced. So this models that phenomena that we can only get so wide before the error phenomena gets overwhelmed. The communication overwhelms is overwhelmed by the error phenomena. Even if P and Q are implementing error correction protocols, they can only surmount the errors up to some proportion of the bits in Q. So if they're far enough apart, we can overwhelm any error correction protocol, right? So that in what is it? 3 lines of code here, 4 lines of code, represents a formalization of exactly those intuitions. And this will, if you run it in simulation, give you the clumping that I'm talking about. It doesn't, this does not address how we then host new agents on top, but that is really a matter of coding, and it must be evolutionary coding. Now let me peel back why it is the case that we might we might expect to be able to encode names as computable reals. Well, an obvious answer is Gödel numbering. So I could take a Gödel numbering on the collection of processes, and that now gives me, because the collection of processes are in bijection with the collection of names, this gives me a representation of names as computable reals. But there's another much cleverer and fancier idea. It turns out that bisimulation generates a pseudo-metric space. You can make it a metric space by whacking it down by an equivalence, but we don't have to go into that here. So then you can take at of P to be the distance from 0 to the bisimulation class of P. Now, there's a mutual recursion going on here, and this recursion hurts my head, right? Because the bisimulation class of P depends on the evolution of P, but the evolution of P, as we notice, depends upon this encoding into computable reals, right? So around and around you go. And I just want to point out that that recursion is very reminiscent of the kind of recursion that you get in the Einstein field equations, where the stress energy tensor is equal to the metric, right? So as the stress energy tensor and the metric interacting with each other starts moving matter and energy around, which changes the metric, which changes the stress energy tensor, and around and around and around you go. So that you have a similar kind of thing taking place in this way of generating the computable reals from the bisimulation equivalence classes. And I make this comment to suggest that rho is also a place where we might consider doing physics. It's getting closer and closer to a place where at the level of rho itself, we could start to consider doing physics. Was there a question? Okay. And to put a little more color on this idea, we could notice that in this version, we have not changed the rate of interaction at all. But in this version, we now have stochastic evolution. So we have a map that's associated with the states. And as we, in the ordinary evolution, where R1 and R2 are within delta of each other, we have just nothing happens to the map. The rate of interaction along R1 and R2 is what it is, whatever it was set up in the map. So nothing changes the map. But we can imagine that in the error case, as they start falling towards each other, right? We're decrementing by delta with each iteration of this rule. So literally the processes are falling towards each other, just like gravity. And here we don't have a gravitational acceleration, we have an exponential acceleration. But one could imagine putting in a gravitational acceleration here. So this changes the rate at which they interact, right? So when we do this state evolution, what happens is that we go and look up the rate at which they were interacting in this state, and we double it. So that's that gives you a sense of the increasing rate of interaction as they get closer and closer towards each other. But you'll note that this is discrete time step, right? So we get this state change in terms of discrete steps in time. What if we wanted to do a more continuous time step? Well, there's a version of rho that is fuzzy. To get the fuzzy notion of rho, we demand an action on processes. So I have some set A, and when I have an A in a process, we kind of multiply. Think of this as like a scalar, right? So this is multiplying this process by some entity or quantity and getting a new process. And we also demand that if I have a pair of names, I can map those into an element of the action. Right. So then I can modify the COM rule in this way, right? So the receiver, the reader, is sitting on X while the writer is sitting on U. And the idea is I use this multiplication, I multiply the two names together, and that gives me some notion of how similar or how far apart they are. And I use that to then multiply against the data that I'm sending to give an amount of the data that's being sent. And that's what's being substituted for Y. And in particular, we could, if we had a measure, mu, right, going from P to A. And so imagine now A is it has at least as much structure as a quantile, right? So this is a nice friendly lattice that we know about, and is a good way to measure information, right? So now if we demand of mu, this measure of information, that whenever A1 is less than A2, then mu of A1 times P is less than mu of A2 times P. Right, now suppose that U1 times X1 is less than U2 times X2, then we have the desired effect from this axiom, right? So we send less information about Q here than we do here. So again, just to make that nice and concrete, what we're saying is this interaction, the X and the U are far apart, right? And so we send less of Q. And these two are a bit closer together, and so we send more of Q, and that's what this is. That's what this is measuring down here, right? So how does that give us continuous transitions? Well, this allows us to implement a slider, right? So imagine now that I fix X and I vary U from some U initial such that UI times X is when I multiply that by Q, I get the process 0. And over here, U final times X, when I multiply that by Q, I get Q back, right? So down here on the left, I'm sending almost no information. And down here on the right, I'm sending more information. So this gives you some partial transition that uses U as a parameter ranging from UI to UF. So the point I'm trying to make here with these different variations of rho in relation to our original question about scaling laws is that we are not programming inside rho-lang. We are programming the rules that make up rho-lang. We're exploring different variations of rho-lang. to tackle this interesting problem of scaling laws for intelligence. And the whole purpose of MeTTaIL, which Christian was just beginning to show off, is to empower this kind of programming. So the MeTTaIL makes it possible to program programming itself in a way that is type safe. So there are lots of ways to program programming itself. Monkey patching in Ruby is a thing, right? But you do not want to monkey patch in Ruby in a production environment. Okay, so so essentially, if you're familiar with the Star Trek universe, right? The meme of the Kobayashi Maru, where it was designed to test the mettle of Starfleet candidates because you couldn't win it, you couldn't beat it, right? But James T. Kirk was the only candidate who went in and hacked the simulation before he took the test so that he could win. And that's really what these last few slides have been about, is since if you can't beat the game, change the rules, right? So this is all Kobayashi Maru territory here. Now I have just a little coda, and then we'll turn it open for discussion. So there are lots of organizations now that are talking about superintelligence, right? In fact, SingularityNet is a member of the Artificial Superintelligence Alliance, and in those implicit and sometimes explicit in discussions, by superintelligence they're measuring against the rod or the yardstick of human intelligence. But I want to propose an alternative definition, which I believe is both effective in the sense that it can be rendered to practice, while at the same time is a relative notion. So it looks like Kevin has a question. Kevin?
Yes, I was thinking about the fact that the scalability, you say, is limited by the error rate between the communication. And isn't the whole fact that we are designing protocol messages, a standardized protocol to reduce the amount of errors in communication? So,
Yes, that is the case, but you can't do it perfectly. That's the point, is no matter what you do, there is no error correction protocol that overcomes all errors at a given distance. That's why you get clumping, right? That's why molecules clump into cells, and cells clump into organisms, and organisms clump into herds and hives and schools.
in analog processes. But I'm talking about simulated digitized processes where you have 100% correctness.
You can't do it. It's not possible because all the digital processes are running on physical hardware, and the physical hardware is subject to all the laws of physics. So it will be, for example, it will be subject to radiation, and that radiation will cause random bit rot. It will be subject to gravitational waves, and that will cause random shifts in distances between components. It will be subject to manufacturing error. It is not possible to have perfect communication over large distances. It doesn't work. In fact, general relativity tells us there is such a thing as space-like distance. Beyond space-like distance, two observers cannot agree on the order of events. So it's hardwired into the physics.
Okay.
Yeah. Okay. So it looks like Kabir, you have your hand raised.
Yes, so my kind of thought is that when we are talking about intelligence, actually, basically errors and forgetting the information or kind of garbling information corruption is like a more, to some extent, it's a feature, not only, it's not a bug, it's a feature.
I agree 100%.
That's how I look at that.
That's what I was trying to say. Precisely. It's a feature, not a bug. Right. the clumping turns into something that we can take advantage of. And that's what I'm trying to get across in these last 3 slides here. So, so the idea of superintelligence that I want to put forward is that superintelligence is when a collection of individual intelligences can deliberately form a coherent collective intelligence. Right? So a few radical rebels get together in order to form a more perfect union. Right? And the individual and collective can engage one another collectively. So the collective intelligence is coherent enough that any individual can talk to it. Right? So a prototypical version of this is slime mold. It's not yet matching my definition, but it's on its way to what I'm talking about when I say superintelligence, right? Slime mold exploits environmental conditions to phase transition to a collective gadget rather than a bunch of individual slime mold cells. Maybe Athens was an example of a superintelligence, and we can play around with those kinds of things all day. LLMs are also a prototypical a superintelligence in that they aggregate over individuals, right? So the Chat GPT and such are aggregates of data stolen from the internet. But the dialogue is frozen in time in that the aggregate doesn't learn post-training, right? So it's on its way to superintelligence, but not quite there, right? Now I want to compare that with what's available in MeTTaIL. Because MeTTaIL is reflective, all of the techniques that we described in those few technical slides may be applied to MeTTaIL itself. So MeTTaIL is a natural framework for AI to explore different patterns of superintelligence. And so now, in the words of Stanley, enough said, and I love to open it up to a conversation. Weaver, go ahead, please.
So I will begin with the slime mold, which is a very good example. The limitation of the slime mold is due to the fact that the intelligent units that construct it are too close to each other. Yes, they are basically too similar. If you compare it to a society of mind or societies, organizations, human social organizations, where each intelligent unit is unique, but then it raises the question of errors in communication and misunderstanding. And so this is like the trade-off between being like a collective intelligence made of very similar units, but with more reliability of communication because they are very, very much understanding each other because they are the same, they have the same experience, more or less the same memories, etc. With very little variations. While if you look at the organization made of humans, in contrast. And I very much agree with you with this direction of direction of how to achieve superintelligence. And the open question in my eyes is whether achieving such a configuration is something that can be achieved in a more or less planned or directed process, or it is something which is really pure emergence. Yes, like no a priori planned or designed trajectory can lead there. So it's more or less, if you look at the space of possible intelligences, how do you search for one like this, which is with the advantage of being much more advanced than others? Not sure if you can create a designed trajectory, but maybe something that is approaching it.
Sorry about that. Internet fail.
Oh.
Yeah. Matt, go ahead, please.
Yeah, I like this overall approach, and I've been thinking about your examples, and particularly the LLM example.
Mm,
And I think it's more than just being fixed in time there. I don't think when we're talking super intelligence, I think it's important to understand the individual constituents.
mm,
Um, that there needs to be some sort right communication. There's a side note there about another math concept, but um, has to be something more, that, in fact, I don't think that there is much communication within the LLM other than my number, statistical number is better than your statistical number.
yeah, all the communication happened during the training.
And there's no back and forth in trying to, I think, consensus
Yeah, right. So if you
comes
had,
into
yeah, if you had back prop,
play
then
there.
yeah, if you had back prop, then you would have back and forth, but in a very weird kind of regimented way. Yeah.
And I think understanding I mean, you can have um, dead objects. I mean, the mathematical concept that came to mind there was sphere packing.
Mm,
When you started talking communication protocols, because that's really what would naturally happen. But there's that clumping, is it a dynamism between individual constituents versus an outer force um, causing um, clumping to happen?
yeah.
And I think in order to have that super intelligence, it has to be in that internal communication.
Yeah, I understand. You think that there needs to be more dynamic, flexible, and internal communication.
Right.
Yeah, that makes sense. Charlie?
Like with purpose underlying that each one kind of trying to argue and come to compromise versus an external force imposing its will on the collective, so to speak.
That makes sense. That makes sense. Charlie, you had a question?
Um, no, actually, I want to argue,
Go
but
for it.
I found I didn't like the response you gave to Kevin because it doesn't seem to me that the absolutism that you seem to be expressing is borne out, right? So bear with me for a minute
Yeah.
on a scale, right? If we're talking about machine computation, right? You mentioned a bunch of different issues, right? One of them was manufacturing errors. So sometime, right, we're capable of understanding the range of manufacturing errors and essentially realizing that and eliminating them for all intents and purposes in if we bring a robust enough process right, obviously it involves really hard work on test suites and all that sort of stuff. You also mentioned distance, right? That communication over a certain distance is always going to be imperfect. But with hardware, we can pack an awful lot of computation into a very small space where gravitational waves aren't going to be an issue, right? We can also understand radiation and what's expected. Yes, we can't predict, a supernova in the next galaxy right, or the nearby in our galaxy, right, happening at a point that, you know, creates a bunch of radiation. But for all intents and purposes, we can measure the expected rate of errors generated by radiation, and we can bound that, and we can use error correcting again to fix that. So what I'm wondering is, why can't we have some sort of a unit as really having perfect communication within the members of that unit, right? Maybe this is what you're arguing for, and I'm
That's exactly what I'm arguing, is that there's a unit, but it's bounded in size. Right? In fact, we know it has to be smaller than space-like distances.
well, I hate that when I argue with you and you tell me that I'm arguing in your favor. So anyhow, good job.
No, I agree. And like as you were speaking, the thing that I was imagining was the communications we have with Voyager. Right? Voyager is getting farther and farther out, right? And uh, like recently they, if memory serves, I could have this wrong, but I think they affected a system reboot because they were getting so much packet loss, right? And it was beginning to show its age, right? That they thought, okay, that's it. But they had this narrow window where they were able to do a system reboot. And after the system reboot, they were able to establish more reliable communication with it and run some diagnostics and extend the life of the communication. But I don't think there's a single NASA scientist out there that thinks that they're going to be able to have stay in touch with Voyager, 20 years from now.
All right, cool. Thanks.
No, good. That's a great conversation. I imagine there's a lot more depth to that. Yeah. Any other questions, comments? Okay, Nabil, please.
Yeah, I just want to ask that I didn't really understand how you used quanta during quantum representation during your communication-based, clampings. So
Yeah.
if you can,
Yeah, happy to go over that again. That's not it's nothing magic or complicated. Okay. All right. So the idea is that if the elements of the action A form a quantole, well, that is a natural lattice for measuring information. So I have all of this algebraic structure, right? So I have a meet and a join, and I have a multiplication. This action is not necessarily that multiplication, but the meet and the join and the multiplication inform this ordering relation, right? And all I'm saying is that being a quantole, having a mu from proc to A is a natural way to measure the information inside a process. And but beyond that, I happen to know, because I know the math of these processes, that there are lots of natural quantiles lying around. So getting a map from here to here is very straightforward. In particular, I also know that there's a representation theorem for quantiles that says that every finitely presentable quantile has a representation as the power set of the set of all strings of some alphabet. So you could think of that as collections of traces. So I can think of all the traces that the process might generate, right? And then the mapping from mu into A is very straightforward. But in this thing, all I'm doing is to say I just want a plausible way of measuring the information in a process, and then I want to have enough structure in A that I can have an ordering relation and then have a hope that that mu will respect this ordering axiom. That's all that's going on with respect to the quantol. Does that make sense?
Yeah, thank you.
Sure. No, good question. Anything else? And again, all of this is just to, like I motivated this slide in terms of the laws of scale. But really, this is just a very interesting class of calculi, and it's not just a single calculus, right? It's an infinite family of calculi, right? And yeah, and this one is an infinite family of calculi, and sorry, this one is an infinite family of calculi. So having a language like MeTTaIL, which allows me to go explore at the calculus level these different kinds of things, right? So that's what Christian was showing you. He was showing you, hey, I can rapidly define a calculus and then go investigate it in terms of a bunch of queries and tools on top of the calculus. And what I'm trying to do is to give you more motivation. Why would I want to do that? Well, exploring things at the calculus level is really important, right? There's some critical ideas that are motivated or motivate us to go and explore things at the calculus level, right? So scaling laws for intelligence is a critical idea, I think, for this community. Superintelligence is a critical idea for this community, right? And having a playground like MeTTaIL, I believe, allows us to go tackle at least some bits of those questions. Charlie, do you have your hand up again?
I do. So now that I'm thinking about this, and yeah, it's great stuff. Where I'm assuming that you have more points that I haven't heard yet around, right now that I understand that you're not arguing against what I think is possible, right? Within a small area, right? An awful lot of computation taking place, right? In ways that obviously have to be developed with, foresight and human intelligence to begin with, right? That, right, on a planetary scale, right, where we've got, the speed of light is a constraint in terms of getting information from, one continent to another, right? And say we've got units like this where we have essentially little super intelligences scattered all over, right? How do we get to the next step, right? And leverage within the constraints of these laws of scale that you've so beautifully shown, right? Something that will allow those super intelligences to reach consensi. Is that the plural of consensus? Anyhow, um, right, on issues, right, that can't be done because of the distance between them. But if we have multiple, right, in the same way, right, you're talking about a hierarchy here, right?
Yep. Yeah,
Um,
exactly. No, you're spot on. So just like we can make I think we can make your question crisp, right? What you're
I wish
arguing
I could.
no, what you're arguing for is that delta could be large. What I was saying is delta can't be infinite, but delta could be large relative to the human scale. It won't be large relative to infinity, but it could be large relative to us humans. And delta is sort of the average size of clustering, right? So above delta, we start adding error rates, and beyond a certain point, the error rates overwhelm the amount of bits in Q. And once that happens, there's no chance in hell that we can recover from the faults, right? So this gives you the region in which it's perfect communication, right? And then beyond that, we can extend our communication in a little penumbra outside of that realm of perfect communication. So error correction allows us to extend delta a bit, and then beyond that, game's over, right? But even though the game's over for this size of agent, it's not over for collections of agents of this size. Because they can, they can be right at the boundaries of these clumps. And so the distance is no longer is no longer what in other words, we get a multiplier for delta. Right. So,
Yeah, now that I understand more, can I back you up through this explanation a little bit farther
sure, go for it.
and go to the screen in which you started out with the computable reals and processes, right?
Okay.
So yeah, that's the one. In one of my question was I didn't understand it. Obviously, you're talking about computable real numbers here, right?
That's
And
correct. Yeah.
there are infinitely more non-computable real numbers, and it seems to me my intuition tells me that there's something important about that that also relates to these scaling laws, right? That
Yeah.
that there's an infinity out there beyond this realm that we're operating in here with this model, right? That
Well, oh yeah, oh yes, oh yes. I'm totally with you. In fact, there are more different kinds of infinities than there are counting numbers. There are more different kinds of infinities than there are real numbers. So there's lots and lots and lots of infinities, right? But our ability to access those infinities and to manipulate them safely is right now limited to what we can do with compute. That's why I restricted myself to the computable reals. Matt, you had a question.
Just one real minor thing that popped in my head. You used delta here
Yeah.
as a fixed value.
Yeah.
And if we look at what's happened through our human history, I would argue that outside factors, technological progress, for example, has resulted in increasing that size of delta quite a
Agreed.
bit.
Yeah. Agreed.
And so that it should not be thought of necessarily as a fixed value.
I agree 100%. I thought about that and I just felt like if I introduce that level of complication at this point, I never get through the presentation. So, but yes, agreed. 100% agreed. Yeah. And in fact,
And how far those are things that are not, you wouldn't have thought of back in the Stone Ages. But what is the limit of the future values? And arguably, there's some physics involved there, but
yeah. I agree. Yeah. I mean,
and I have to drop. So
well, thank you so much for your comments. Kevin, you had a question.
Yes, on that topic, I saw in your Roland design that your numeric data type is a 32-bit signed number. Is there a reason that you chose that?
There was at the time. I mean, we're in the process of upgrading a lot of that stuff as we port to Rust. But that there were good reasons at the time that we did it, but it's not it's not a hard fast um thing. We can certainly shift to a different data type. It will cause I'm sure a little bit of ripples in the code as we swap it around, but that was that's mostly an artifact of Rolang being developed over a decade ago.
Because I'm assuming if we move to a higher representation with more bits and potentially fixed point instead of floating point, that the error rate which you use as your limitation to scale goes down.
Sure. Yeah. I mean, like I said, I haven't fixed delta, right? Delta could be large relative to humans, but delta can't go beyond space-like distances, right? So I'm trying to argue in the absolute, right? And then we can once we sort of made our arguments, how do I say? We have a block of stone. We've just chipped away a bunch of the stone that doesn't look like the David, but we haven't done a lot of fine chisel work. Right. That's kind of what these arguments are like here. It's a bit of sculpting. But thank you for the point you've raised, for sure. All right, we're just a minute past the bottom of the hour. Is there any other questions, comments that need to be addressed here today? Burning questions?
Is it possible to have to get your documentation on the slides?
Absolutely, yeah. The slides are already up on the cloud. Let me give you a link for that. Just 1 second.
Is this the same version that you uploaded last week to?
That link keeps pointing to the updated file. So the one that I put up on Mattermost is there.
Okay.
So you can just grab it, but I'll also make it available here and now if that went past people on Mattermost. Okay. All right, we got a chat, and there's that. Okay, so that's that, and then I'll make the video available as well. Anything else we need to cover at this moment?
Define need.
Leave that to the experts. All right, folks. Thank you so much. Have a great rest of your Tuesday, and see you next week.
Thanks, Greg.
Thanks very much, Greg.
Thanks. Bye.